you. So yeah, first of all, I wanted to thank the organizers for organizing such a nice conference and inviting me. I feel like I learned a lot, and it's been a lot of fun. And I got to see a fire truck, so that was good too. Okay. Okay, so I'm going to start with I can tell that. Okay. I'm going to start with the theorem of Gromov. Okay, and it says the following. Let M be a smooth manifold. Kappa from M to R. This is a continuous function. Okay, and so suppose I have the following situation. Okay, so I have a sequence. This is a sequence of Riemannian metrics, and they're converging to some limiting metric. Okay, so these are like C2 Riemannian metrics, but I'm only going to assume uniform convergence. Okay? And then also I'm going to assume that each metric in my sequence satisfies a lower bound on the scalar curvature, and I'll allow that lower bound to move around. Okay? So the scalar curvature of each gi at x is bounded below by kappa of x for all x in M. Okay, so remember, this is a continuous function, so this is some moving lower bound. Okay, and so then the conclusion of this theorem is that then this limiting metric, remember the limit is C2, the limiting metric also has scalar curvature bounded below by kappa. Okay, so somehow this is rather surprising. I mean, okay, we know the limit is C2, but here we are only assuming uniform convergence, so a priori you would not really expect to be able to say very much about the curvature of the limit, and yet these pointwise lower scalar curvature bounds are preserved. Okay, and sorry, I just wanted to mention, so recently, okay, for brevity, I will just write something very short. Okay, so recently it was shown, this is by Yiqi Huang and Man-Chun Lee, that in the same setup, the result is also true if you replace this condition by a local n/2 condition. Okay, so also true if instead you just have, how did I write this? That you have the negative part of the scalar curvature minus kappa. This is going to 0 in Ln/2 loc. Okay, so this is an improvement because this condition is replaced. All right, so anyway, but okay, let's talk about Gromov's theorem. So, if you wanted to prove this, you could proceed in one of two ways. There are two proofs that I know of. And so the first is due to Gromov. I need to switch my notes. The first is due to Gromov. Okay, so first, I will try to explain this. First, I'm going to say something vague, okay, and then I'll maybe explain a little more. Okay, so this is method 1. How do I want to write this? So this is the original proof due to Gromov. And so basically what he does, correct, yeah, so this condition is replaced entirely by this.
K still function. No.
Oh, I think it is still a C0 function, but I could be wrong. We can look at it again. Yeah. Other question? Okay. So somehow what Gromov does is that he notices, we've seen a little about this in some previous talks, that this lower scalar curvature bound can kind of be understood as a C0 condition. And then if it's a C0 condition, somehow, then it's actually like not that surprising that it's preserved under uniform convergence. Okay, so now I will write something vague, and then I will say something a little more precise. So what you could say is he sort of creates this generalized notion of a lower scalar curvature bound that makes sense for C0 metrics. Okay, and then since we're proving something about C0 limits, it's going to be stable under C0 convergence. Okay, And then, of course, it should agree with the normal notion of a lower scalar curvature bound if you have a C0 metric that's actually C2. Okay? So this agrees with the usual notion for C2 metrics. Okay, so given such a definition, obviously it's like very hard to come up with what this is supposed to be. But given such a definition, here's how you would prove this theorem. Well, my GI satisfies some lower scalar curvature bound, in the normal sense. These are C2 metrics. And so they're also going to satisfy this lower scalar curvature bound in this generalized C0 sense. But then the C0 definition is stable under uniform convergence. So the limit is going to satisfy this lower scalar curvature bound in this sort of generalized C0 sense, but then, the limit is C2, so it will also satisfy the classical lower scalar curvature bound. Okay, so how does he do this? So, I'm not an expert in this area, but many people here are an expert in this area. And so back in 2014, Gromov had a proof of dihedral rigidity for cubes. Okay, and so thanks to dihedral rigidity, we know that in a Riemannian manifold with non-negative scalar curvature, you cannot have a cube that has mean convex faces and strictly acute dihedral angles. Okay, and then actually, conversely, he showed that if you have negative scalar curvature, you will have cubes like that. And so you could actually take the non-existence of these cubes to be the definition of non-negative scalar curvature. Okay, and then, moreover, okay, mean convexity can sort of be understood as a C0 condition. So then you can like use this to be the generalized definition for metrics that only have C0 data. Okay, so this is basically how Gromov does this generalized notion. Okay, but yeah, I'm not an expert on this, so I won't talk any more about this. Okay, and so what I will talk a little bit more about is the second method of proof. And so this is due to Bamler. All right, and this proof uses Ricci flow. Use Ricci flow. Okay, so I'm sure now we've seen this a few times, but let me just remind you what is the Ricci flow. The Ricci flow is an evolution equation for Riemannian metrics on a manifold. It is this evolution equation. So the time derivative of the flow is equal to negative 2 times the Ricci curvature of the flow. Okay. And then we can prescribe some initial data. Yeah, and so, maybe it's not clear why the Ricci flow would have anything to do with this theorem whatsoever. But maybe if you're a little more familiar with the Ricci flow, you might guess that it's relevant. And this is due to the fact that lower scalar curvature bounds are preserved under Ricci flow. Okay, so we've already seen this, but let me just remind you. Okay, and by this I mean constant lower bounds. So if my initial data let's call it G naught, has scalar curvature bound below by some constant kappa naught, then for all times greater than 0, the scalar curvature of each time slice of the flow is also going to be bounded below by kappa naught. Okay, so this is for all t greater than 0 for which the flow is defined. All right, and so if we wanted to prove this theorem of Gromov using Ricci flow, now I'm going to actually lie to you quite a bit, but maybe this will just be helpful to get an idea. So if I wanted to prove this theorem using Ricci flow, let me maybe just do it in the case where kappa is a constant. So here is how I could argue. All right, so I have my sequence of metrics. They're converging uniformly to some limiting metric. Okay, and so these satisfy some lower scalar curvature bound. Okay, and now I want to conclude that the limit also satisfies this lower scalar curvature bound. So what can I do? Well, I can run the flow starting from each metric in my sequence, and I can also run the flow starting from the limiting metric. Okay, and then somehow, hopefully the flow will turn the uniform convergence of the initial data into locally smooth convergence of the flows for positive times. Okay. So this is not clear that this would happen, but luckily this is kind of what happens. This is for positive times. Okay, so now I want to prove this theorem where this is a constant. Okay, and so each metric in my sequence satisfies this uniform lower scalar curvature bound. The uniform lower bound is preserved along the flow, so for all positive times, these flows satisfy the lower scalar curvature bound. And then I have locally smooth convergence for positive times, which means the limiting flow for positive times also satisfies this lower scalar curvature bound. And now I can let t go to 0, and I'll get the conclusion. Okay, so yeah, okay, I told you a lot of lies. in this little sketch, but maybe this can illustrate a little bit of why you might guess that Ricci flow is relevant to this theorem. I think so. I mean, I guess you need to have enough regularity to have this be true, but it should be.
Why is this last arrow more believable than the first arrow, the initial arrow?
Which last arrow?
The last arrow that's going up,
Uh-huh.
going that backwards. Why is that easier than the initial arrow? Because the convergence of GT to initial data, that's probably also only C0, right?
Yeah, well, if your initial data is C2, then it will turn out to be C2.
Oh, okay.
But yeah, I agree, it's not. I didn't explain that, yeah. Okay, other questions? All right, so now we have these two proofs of the same theorem. We have this sort of generalized definition involving cubes due to Gromov, and then we have this Ricci flow proof. And these techniques don't apparently have much to do with one another. So this leads us to ask whether there's some underlying connection between the two of them, or if we can somehow understand the relationship between the two of these. Oh.
Isn't this for complex?
Yeah, I didn't, so I don't, you have to localize this, which is actually quite hard. Yeah, but I didn't explain that.
Is that like what was done?
Yes. Yeah, and so basically what he does is he says, okay, like if you have a lower bound at a point, you can find a neighborhood of the point where you have like almost that lower bound, like minus an error. Then you can like glue this into Euclidean space and you can run a Ricci flow, or actually a Ricci to flow. But yeah, this is kind of dicey. Okay, so let me write a motivating question.
You're saying, for example, theorem, if you choose a function.
Yeah. Is this true? No.
So his method only would work.
No, he like somehow localizes this argument. Or okay, how do I say this? So he basically reduces this case to the constant case by saying, okay, if I have a lower scalar curvature bound at a point, I can find a neighborhood of that point in which I have, like kappa of x naught minus delta. Now this is like a uniform lower scalar curvature bound on a neighborhood of the point. Let me take a very small neighborhood, I'll glue it into Euclidean space. Now I can run a Ricci to flow on Euclidean space, and I'll use heat kernel estimates. Okay, I haven't said anything about this, but I'll use some estimates to show that, under that flow, it's not going to go down too much.
And then it goes back.
Goes back.
For function. So you just put this.
Yeah, so you just do this at every point.
That gives you the general.
Yeah. Okay. Okay, let me erase all of this.
Can you do this for more general functions using a density argument?
Using a density argument. Sorry, for what other kinds of functions? Oh, like L infinity or something. Or I guess not L infinity, but. I don't know. Yeah, that's an interesting question though. Yeah, I don't know. Okay, I mean, like somehow you need to know that in a neighborhood you're not going to, but okay, maybe if you go down on a very small set, that's actually not a problem. I'm not sure. Yeah, that's true too. Okay, then I would, yeah, maybe you should be able to do something like that. I guess, okay, so you also need to be careful. You need to make sure you also have enough regularity. Oh, but that's just for the function. Okay, yeah, so yeah, maybe something like this could work, but I'm not sure. Were there other questions? Sorry. No, okay. Okay, let me write down a guiding question then. So, okay, so the question that is sort of motivating this talk is whether this definition of Gromov, this sort of generalized notion of a lower scalar curvature bound involving cubes, can be reformulated in terms of Ricci flow. So in other words, whether there's a statement about Ricci flows that somehow is equivalent to this statement. Okay, actually, so before I continue, I wanted to just write down some other notions of non-negative scalar curvature for non-smooth metrics that other people have been working on. And so, for instance, we have this nice one of Dan, Lee, and LeFloc. That's not right. Okay, and so these are for metrics that are also at W12 loc, but they don't have to be C0. Okay, and then recently, people have studied Ricci flow coming out of spaces with non-negative scalar curvature in this sense. Okay. And so those people were Jiang, Sheng, and Zhang. This is Huayu Zhang. So this is in 2021. Okay, and then also Lam and Simon have a notion of non-negative distributional scalar curvature for metrics in W22. And they have some nice work on Ricci to Turk flows coming out of these spaces. Okay. '21, yes. Okay, so I think a lot of this work has maybe a slightly different flavor than what I'm going to talk about today. These use distributional derivatives, which I don't use, but yeah, there's a lot of interesting stuff in this story. Okay, so I'm trying to answer this question of whether this definition of Gromov's can be reformulated in terms of Ricci flow, or in other words, can we somehow use Ricci flow to define, for a metric that only has C0 data, to define what it means to have a lower scalar curvature bound, in a meaningful way, and and whether that is equivalent to Gromov's definition. And so, okay, so I don't know the answer to this question, but at least kind of a first step towards answering this question would be to use Ricci flow, somehow to define what it means to have a lower scalar curvature bound at a point for metrics with only C0 data, and then sort of show that that definition behaves how you would like. And so that is going to be the goal. I don't know where to write. Okay. Okay, so goal. Develop a reasonable pointwise notion of a lower scalar curvature bound for C0 metrics using Ricci flow. Okay, so any reasonable definition should satisfy certain items, which I'm now going to tell you. Okay, so first of all, if I have two metrics that agree to greater than second order at a point, then one of them should satisfy a lower scalar curvature bound, in this generalized sense, at that point, if and only if the other one does. Okay, so what I mean by that is if G prime and G prime prime are two C0 metrics, such that the following is true. Okay, so let's measure this closeness with respect to some, fixed smooth background metric. Okay, so what I'm saying is in a neighborhood of some point x0 that I'm interested in, if the difference of these two tensors is bounded by some polynomial in the degree of strictly greater than 2 in the distance of x to that point, then the scalar curvature of G prime should be bounded below by kappa at x0. Okay, so this is the point we were interested in, if and only if the same is true for the other metric. So if and only if the same is true for G prime prime. Okay, so this looks a little complicated, but this is actually a very natural condition. Why is this a natural condition? Well, if these were smooth metrics, we could just look at the Taylor expansions around the point x0. Okay, and if this condition were true, this would tell us the 0 first and second order terms in the Taylor expansion were all equal. Okay, so in other words, the 0 first and second order derivatives of those metrics at the point x0 were all equal, and so in other words, the scalar curvature should be equal. Okay, so this is a C0 condition, but in the smooth case, it implies that the scalar curvatures are equal at x0. And then second of all, okay, this is quite natural. I want uniform lower scalar curvature bounds to be preserved along the Ricci flow, since that is what is true for smooth metrics. Okay, so in other words, if my sort of generalized notion, which I haven't told you what it is, if this holds at every point, then I want to, and if I can somehow find a Ricci flow starting from my C0 initial metric, then I want, the classical lower scalar curvature bound to be to hold at every positive time. So, okay, I said that in a very rambling way, but maybe I will write it precisely now. So if G is a C0 metric on, let's say, a closed manifold M, such that scalar curvature of this C0 metric is bounded below, in this generalized sense, everywhere. And if I have a Ricci flow that's sort of starting from G, okay, so I need to explain to you what does it mean to have a Ricci flow starting from C0 initial data. Okay, we'll get to that. So, and if I have a Ricci flow, if tilde GT is a Ricci flow starting from G, okay, so this is in quotes because I have not explained this yet. Then I want all time slices of my Ricci flow to satisfy the same uniform lower scalar curvature bound. Oh, sorry. So this is a constant. Okay. And the scalar curvature of all time slices of the flow are bounded below by kappa naught. And this should hold for all positive times for which the flow is defined. Okay, so this is basically the C0 analog of this nice classical fact that uniform lower scalar curvature bounds are preserved under Ricci flow. But also, let me maybe sort of say another thing about this point. So, the sort of like toy proof using Ricci flow of Gromov's theorem that I have now erased, this suggested to us a very natural definition of a uniform lower scalar curvature bound for C0 metrics. Namely, we could declare that my C0 metric has a particular uniform lower scalar curvature bound if for all positive times a Ricci flow starting from that metric satisfies the classical uniform lower scalar curvature bound. But Gromov's theorem is a local statement. It is a statement about lower scalar curvature bounds at a point. So how do you localize that uniform definition that I gave you? Okay, or in other words, what is a pointwise definition such that if it holds at every point will imply the global definition? Or in other words, what is a pointwise condition such that if it holds at every point will tell you that for all positive times the Ricci flow satisfies the classical lower scalar curvature bound? Okay, so that is what this point is getting at, is that somehow we want to localize the very natural uniform Ricci flow definition. Okay, and then of course, I want my notion to agree with the normal notion of a lower scalar curvature bound if I have a C2 metric. So I will say, okay, so agrees. This one is not hard. Okay. Maybe I will also, this is not so important, but I will just make a remark that there's sort of a tension between these two. Okay, because if I make my definition, something more restrictive, then it's easier to prove this one because I'm assuming something stronger. Okay, but then it's harder to prove this one because I need to conclude something stronger. So somehow you need to balance. I don't know. You need to find a right definition to balance these two. Okay. Okay. So now, I've been telling you that I would like to use Ricci flow to define a lower scalar curvature bound for C0 metrics. And so now I owe you an explanation of what it means to have a Ricci flow starting from C0 initial metrics. And so now I'm going to tell you what that means. And first, okay, so let me just write this. So henceforth, I will take M to be closed. Compactness is actually not essential. Well, okay, I'll say a little bit about this in a minute. Okay, so now I'm going to tell you what it means to have a Ricci flow starting from C0 initial data. Now, in the smooth case, what it means is that you have a smooth solution to the Ricci flow equation, and the time slices converge smoothly to the initial data, or locally smoothly if you're on a non-compact manifold. Now we only have C0 initial data, so obviously that does not make sense. But at the very least, we could maybe hope that we could find a Ricci flow whose time slices converge uniformly to the initial data as t goes to 0. And so this next result that I'm going to tell you is that actually that is also too much to hope for. But at the very least, you will be able to find a Ricci flow that converges uniformly to the initial data modulo pushed forward by a family of diffeomorphisms. Okay, so lemma. Okay, so let M be closed. I already said that. Let G be a C0 metric on M. Okay. Then there exists, okay, so first of all, there exists a Ricci flow. So there exists a time-dependent smooth, I guess, family, okay, time-dependent family, smooth family of smooth metrics. GT. Okay, these are defined for t in some positive time interval strictly greater than 0. And, okay, this part is not so nice. And there exists a continuous surjection chi from M to M. This is a continuous surjection such that, okay, so first of all, okay, so my time-dependent family of metrics, obviously we want it to be a Ricci flow since I'm trying to find a Ricci flow for C0 initial data. Okay, so yes, so this family is a Ricci flow. So I will say solves the Ricci flow equation. And also, okay, so the conclusion was going to be that this Ricci flow converges uniformly to the initial data modulo pushed forward by a family of diffeomorphisms. Okay, and so that's what I'm going to write now. Also, there exists a smooth family of diffeomorphisms chi t. This is defined in the same time interval such that the chi t converge uniformly to this continuous surjection chi as t goes to 0. And the push forward of the Ricci flow, so chi t push forward the Ricci flow tilde gt, this thing converges uniformly to the C0 initial data as t goes to 0. This goes to 0 as t goes to 0. Okay. Moreover, I'll write it up here. Okay. Okay, and so, yeah, what do I want to say? Okay, moreover, these things are unique up to isometry. Okay, and so how do I want to say this? So, moreover, okay, so this thing, I call this a regularizing Ricci flow for G, and the reason I say it's regularizing is because the initial data was not smooth, but now we have a smooth Ricci flow for positive times. Okay, so this is not important that I call it this, but I guess I'll write on the sideboard, this is called a regularizing Ricci flow. Okay, and so if I have another regularizing Ricci flow for my metric, another regularizing Ricci flow, in other words, another thing that satisfies these items, then that thing will be isometric to the first regularizing Ricci flow. Okay, so if tilde, oh my gosh, I'm too short for this. Tilde gt prime chi prime is also a regularizing Ricci flow for G. Then there exists a diffeomorphism alpha such that this is a stationary diffeomorphism, such that pullback of tilde gt is equal to tilde gt prime, and chi precomposed with alpha is equal to chi prime. Okay, and so this, remember, a regularizing Ricci flow here is a pair. It's a pair of a Ricci flow and also this continuous surjection. This is not so nice. Yeah, those are Ricci to Turk flows, and so. So yeah, so this is pulled back, and so now we're looking at what happens to that. I mean, ordinarily for a smooth Ricci flow, you can just make the initial data identity, so you don't have this. So this is studying, what happens at the initial data. Also, this uniqueness statement, I believe, requires some estimates that were not available at the time of this paper. Yeah, this is. Okay. Okay, so I mean, I should just say, like, for this talk, I have everything stated in terms of Ricci flow. I think people maybe are a little more familiar with Ricci flow. But you could also, and actually this tends to be my preference, you could also just work with Ricci to Turk flow. This is a Ricci to Turk flow. And so this object is called a Ricci to Turk flow. I will talk a little more about this later. This satisfies a very nice flow equation. It's very nicely behaved analytically, okay? So yeah, so every statement that I make about Ricci flows has an equivalent statement in this talk in terms of Ricci to Turk flow. And okay, so I had assumed compactness, and then I erased it. And so the compactness is needed for this part, but if you just wanted to work with Ricci to Turk flows, the compactness is not so essential. Okay.
You might have meant to spell why is it continuous surjection not?
Homeomorphism. Yeah, it's horrible, right? Okay, so okay, actually, I will answer this. I'm gonna write something down. And so we know sometimes homeomorphism, thanks to some recent work of Lamb and Simon. Okay, so Lamb and Simon. This is in 2021. Oops, 21. They said for some four manifolds. Okay, and these are going to be Riemannian metrics that have small w22 energy. Okay, we may actually take chi to be a homeomorphism. I actually suspect, though, that there are counterexamples in general. And so the concern is that somehow, what are these diffeomorphisms? These diffeomorphisms are going to be generated by a particular vector field. The vector field will depend on a first derivative of this Ricci to Turk flow. Okay, and if the initial data for this Ricci to Turk flow is only C0, that vector field could become degenerate at time 0. So the chi t are generated by some x, which depends on like first derivative. Okay, sorry, these are not equal. This is okay. And this is going to be bounded by something like c over root t. Okay, so the concern would be that somehow like the trajectories of these flows, maybe they, this is supposed to look like square root of t, maybe they kind of converge like this. Now for Lamb and Simon, I believe, their flows actually always have some estimate like this. And so this is definitely not going to happen. Like the worst case scenario is not going to happen. So I don't know. I kind of suspect there are counterexamples, but I don't know. But anyway, if you just work with Ricci to Turk flow, you don't need to worry about this. So that's another advantage of working.
The follow-up question, even though I asked that, is, do we actually care? Like, are there applications where you'd want it to be more or not particularly?
I don't know. I mean, I don't know of any, right? I guess. I mean, I think it's interesting. Like, it's interesting for knowing about Ricci flows, but I don't know. Yeah, I don't know any applications. I will, like, in this context, okay, there are some advantages to working with Ricci flow because maybe it's a little easier to see what's going on geometrically. But even in those cases, I think you don't really need to know what happens in the initial data. So, yeah. Okay. What time did we start? Okay. I have some time. Okay. Great. Okay, so remember the original goal of this talk was to somehow use Ricci flow to define what it means to have lower scalar curvature bound at a single point if you only have C0 data for your metric. And so, and first in order to do that, I needed to tell you what it even means to have a Ricci flow starting from C0 initial data. And so now I've done that. This is what it means. Okay, and so now I'm going to use this information in order to make the definition. Okay, and so the idea is that if I want to identify whether my C0 metric satisfies a particular lower scalar curvature bound at a point, what I can do is, well, okay, so this flow is regularizing, it smooths out the metric. So what I could do is I could somehow, look at the smoothed out metric and then check whether this sort of smoothed out flow as t goes to 0 satisfies a similar lower scalar curvature bound near the point I'm interested in. Okay, and so let me maybe just write precisely what it is. Okay, so definition. Let M be closed. G a C0 metric on M. Okay, so now this is going to depend on a parameter. I don't think, I'm not so happy with the range of this parameter, but that's okay. So for beta between 0 and 1/2, we say G has scalar curvature bounded below by kappa at x in the beta weak sense if there exists a regularizing Ricci flow tilde gt chi for G and remember that unfortunately this chi was just a continuous surjection. Okay, so and there exists some point y in the pre-image of x under chi for which the following condition holds. Okay, so this looks a little technical, but I'll try to break it down once I write it down. So we take the infimum over all positive constants. This is not important. This is for scaling. Okay, and then so basically what we want to do is we want to let t go to 0. So let's take the lim_inf as t goes to 0. And as t goes to 0, then I want to look at the scalar curvature of my smoothed out metric. So I'm going to look at the scalar curvature of the time slices of my Ricci flows near the point that I'm interested in. Okay? So, and I'm not just going to look at the scalar curvature of the time slices of the Ricci flow at a single point. Actually, I'm going to look in a small time-dependent neighborhood of that point, and the size of this neighborhood will go to 0 as t goes to 0. Okay. Okay, so this is the point. Okay, now I need to explain this. So this is a ball of size slightly larger than square root of t. So beta is less than 1/2 and t is going to be very small. So t to the beta is slightly larger than square root of t. The scalar curvature of the time slices of my flow. Okay, and so how many parentheses? 1, 2, 3. Okay, so okay, so what is this saying? What this is saying is that I will declare that my C0 metric has a scalar curvature bound, a lower scalar curvature bound, at the point x, if after I run the regularizing Ricci flow and I look at the time slices of that regularizing Ricci flow in this neighborhood of size slightly larger than square root of t around this point, and so as t goes to 0, if as t goes to 0, the scalar curvature of the time slices of the regularizing Ricci flow are bounded below by kappa naught, then I will say that that means that the initial data had scalar curvature bounded below by kappa naught at x. Okay. Why here am I looking at this point y, which is in the preimage of x under chi, if I'm trying to define a lower scalar curvature bound at the point x? The reason basically is because of this sort of twist where we don't have a flow that converges uniformly to the initial data. We somehow only have uniform convergence after push forward by this family of diffeomorphisms. And so somehow this is here to undo this family of diffeomorphisms. Okay. Okay, so, I made some choices here. First of all, as I mentioned before, there could be multiple choices of regularizing Ricci flow for a C0 metric. Also, this is just a surjection, so there could be multiple y in the preimage of x under chi, but actually this definition is independent of those choices. Well, okay, it breaks the scaling, unfortunately, which is why we have to put this thing here. If beta were 1/2, then you wouldn't have to have this here because of parabolic rescaling. But the reason that beta is smaller than 1/2, strictly smaller, is because in the proof that I have of one of the later results, I use some heat kernel estimates. Okay, and so it will turn out that it's nice to have beta strictly smaller than 1/2 then, because outside a ball of radius t to the beta, the heat kernel at time t will decay exponentially. Okay. So now I've erased what we want to be true about this definition, but I will just remind you, we want this definition to be stable under greater than second order perturbation of the metric. And then if this holds everywhere, we want for positive times the regularizing Ricci flow to satisfy a uniform lower scalar curvature bound. Okay, so now I'm going to write down 2 theorems that tell you that both of those things are true. Okay. All right. Okay, so this first theorem is going to tell you that this definition is stable under greater than second order perturbation of the metric. Let M be closed. G prime, G prime prime, C0 metrics on M that agree to greater than second order around some point. Near x naught. Okay, so then there exist regularizing Ricci flows for G prime and G prime prime respectively. So I will call these tilde G T prime chi prime, tilde G T prime prime, chi prime prime, such that for beta, in this interval smaller than 1/2, if C is greater than 0, then for T small, depending on C, we have the following. Okay, and so what this is going to, this result just says that in a ball around the point that we're interested in, of radius c t to the beta, the scalar curvatures of the push forwards of these flows by the appropriate families of diffeomorphisms, those scalar curvatures will stay close. Okay, the scalar curvature chi t prime, gt prime. Okay, so this difference will be bounded above by some small positive power of t. Okay, so in other words, this right-hand side goes to 0 as t goes to 0. This looks a little bit messy. Again, I'm going to make an advertisement for Ricci to Turk flow. So if you work with Ricci to Turk flows, this is just going to say that if you have 2 pieces of initial data that agree to greater than second order around some point x naught, then the scalar curvatures of the Ricci to Turk flows starting from those pieces of initial data will stay close in this ball of radius t to the beta. Okay, so maybe it's not so clear to see, but it's actually fairly straightforward once you have this result to show that this definition is then stable under greater than second order perturbation of the metric. Okay, and then the second theorem I wanted to tell you is that, it isn't, so what we wanted to be true is that if this held everywhere for some constant, then for any Ricci flow, any regularizing Ricci flow starting from my initial data, all positive time slices of that regularizing Ricci flow should satisfy the classical uniform lower scalar curvature bound. And so now I will write the theorem that says that that is indeed true. Okay. Sorry, Ricci to Turk flow. Okay, I will put it up here. These are the Ricci to Turk flows, which I haven't told you what the Ricci to Turk flows are, but I will. Okay, so let M be closed. G is C0 metric on M, and suppose there exists some beta between 0 and 1/2 such that the scalar curvature of my metric is bounded below by some constant kappa naught in the beta weak sense everywhere. Everywhere, okay. Then if I take any regularizing Ricci flow for my initial metric, I'm going to suppress the chi, so if tilde gt is a regularizing Ricci flow for my initial metric G, the scalar curvature of tilde gt for all positive times for which this flow is defined will also be bounded below by kappa naught. Okay. So in other words, uniform lower bounds are preserved under the regularizing Ricci flow. Sorry, I realized just as I was writing this that I forgot to say something very important about this theorem, which is like here I have stated it as if I have two metrics on the same manifold. But actually, you can prove a version of this result if you have two metrics on different manifolds that just agree to greater than second order in some coordinate chart. Okay, so this is truly a local statement. It doesn't depend on the topology of your manifold. Okay. Let's see. I think I have maybe 10 minutes. Okay, so in the interest of time, what do I want to tell you? I think one thing that might be instructive is if I tell you a little bit about the proofs of these two results. Okay. Yes, I'll tell you about the proofs of these two results, but first I will have to tell you a little bit about how to construct a regularizing Ricci flow, and that will sort of help us understand this theorem as well. Okay. And so, if you're someone who studies Ricci flows, what you know is that if we're trying to find a solution to the Ricci flow equation for some initial data, even if the initial data is smooth, one thing that we often have to contend with is the fact that the Ricci flow equation is not strongly parabolic. Which would be nice. It would be nice if it was, because then we would expect to have some nice, we would expect the analysis to be nice. But anyway, it's not. And so one way to get around this is to do this trick due to de Turk, which is that we first solve sort of a related equation to the Ricci flow equation that is strongly parabolic, and then somehow, if we pull back that solution by a family of diffeomorphisms, this will turn into a solution to the Ricci flow. Okay. And so here is the related equation that we solve. This is the Ricci to Turk flow, which I keep talking about. Okay. So here is the Ricci to Turk flow. Okay. And so, okay, I can prescribe some initial data. And so the way that I've written this doesn't look like it would be any easier to solve than the Ricci to Turk, than the Ricci flow, but it turns out that it actually is. It's better behaved analytically. Okay, and so you can just check. So here X is some time-dependent vector field, and if you manage to somehow solve this, and then you pull this back by the family of diffeomorphisms generated by X, you will indeed get a Ricci flow. And so what we want to do right now is we want to show that there is a regularizing Ricci flow for C0 initial data. And so what we need to do is we need to first of all show that there's a solution to the Ricci to Turk flow for C0 initial data. And then once we have that solution, actually it would be fairly straightforward to pull it back by some family of diffeomorphisms, generated by a vector field, and this will give us the regularizing Ricci flow. Okay, so really what we need to do is we need to show that there exists a solution to the Ricci to Turk flow starting from C0 initial data. Okay, and this is quite a well-studied problem. So let me write some results. So the first results of this type, we've talked about these, are due to Miles-Simon. Koch and Lamb also had some results. This is 2012, 2015, okay, and then, okay. So Koch and Lamb, sorry, so Miles-Simon, let me first write some statement. Okay, so for C0 initial data, there exists a smooth, short time solution to the Ricci to Turk flow that also converges uniformly, or if you're on a non-compact manifold, it'll converge locally uniformly. That converges uniformly to G as T goes to 0. Okay, and so, yeah, so Miles-Simon was the first to prove any results like this, and then Koch and Lamb proved, okay, so Miles-Simon also had some nice derivative estimates. Koch and Lamb on small perturbations of Euclidean space, used a sort of a different method to construct solutions that give you slightly better derivative estimates. And then I showed that this method of Koch and Lamb can be put onto manifolds if you use a Ricci flow background. Okay. But anyway, so I want to, okay, so what this tells us is that if we have C0 initial data, we can find a solution to the Ricci to Turk flow that converges uniformly to that C0 initial data. And then, then once you pull this back by some family of diffeomorphisms, I'm going to sweep the details under the rug, but this is not hard, then you will get this regularizing Ricci flow that I've been talking about. Okay. And so now I want to talk a little bit about this method of Koch and Lamb, because I think it also helps to explain why this result is true. Okay, so this is the result that says that if your two metrics initially agree to greater than second order, then the scalar curvatures of the Ricci to Turk flows for those metrics will stay close. Okay, and so, okay, so how should I do this? Okay, so okay, fine. Okay, so they prove their result using a fixed point argument. And in the course of doing that, so this is due to Koch. They prove an estimate that looks like this. Okay, so here is the Ricci to Turk flow that you're trying to construct. And here, they work on perturbations of Euclidean space, but you could take this to be like a background Ricci flow. So this is some background metric. This is smooth. Okay, and so what this is saying, okay, let's assume that your initial data is close to the background metric in C0. Then it will remain close for positive times to the background metric in this X norm. This is what the result is saying. And so this X norm, I will not write down what it is, okay? But it has sort of a local, okay, I just won't write it down. It has a local L infinity part, which is the relevant part for us. Okay, and so remember, okay, so what they showed is that if you have initial data that is close to a background metric in C0, then the Ricci to Turk flow will stay close to that background metric in some sense for positive time. Okay, and so what we want to show is if we have two C0 pieces of initial data that are close, not just close in C0, but actually close in the sense that they agree to greater than second order, then we want to show that the Ricci to Turk flows will stay close in the sense that their scalar curvatures will stay close. Okay, and so somehow like inspired by this this nice result of Koch and Lamb, what we could do is we could somehow, okay, so we have two pieces of initial data that are close. So we're not interested in closeness to a background metric. We're interested in the closeness of two pieces of initial data. Okay, so okay, so here are my two pieces of initial data, and they're not just close. Okay, I should erase this now because this is just my weird thing that I'm doing. So now these two pieces of initial data are not just close in C0, they are close in the sense that they agree to greater than second order around some point. So what I will do now is I'm going to put some weight onto here. Okay, and so this weight is going to be finite precisely because they agree to greater than second order at x naught. Okay? And so, okay, so for my estimate to be true, I'll pick up something finite, that's fine. And so what is this weight? Well, if my two metrics agree to greater than second order around x naught, that means that that this is true, that their difference around x naught looks like this. Okay, so this is 2 plus eta. Okay. And so basically here, I will just make this weight, which is 1 divided by this picture. Okay, so, okay, and so I need to figure out what to put on this side. Like somehow I have this nice result of Koch and Lamb, and now I'm putting weights onto it. And so somehow if I put some weights onto this norm, I would like to get some estimate, and this is going to be a weighted estimate because, I want to show that the scalar curvatures are close, which means I want to show that, they basically, the two Ricci to Turk flows are basically going to continue to agree to greater than second order. Okay, and so I'll have to put some weight on, and the weight is going to be time dependent. Why? Well, if I take this picture, okay, so remember this looks kind of like this picture. If I were to evolve this picture by the heat, something parabolic like the heat equation, this picture is going to draw in, in this region, the picture will draw in some heat from out here. Okay, and so the weight is going to increase over time, or the weight needs to be less aggressive over time because the two solutions will diverge a little. Okay, and so here is the correct weight. Okay, so over time, this weight is getting less aggressive because I'm going to add a square root of t here. I'll divide this. Okay, and so this statement is going to tell me that if I have two C0 initial metrics that initially agree to greater than second order, then basically they're going to continue to agree to greater than second order for some small times. Okay, and so then once you have this weighted estimate, it's actually fairly easy to show that the scalar curvatures will also stay close. Okay, maybe I have 1 minute. I have 3 minutes? Okay, great. I can say something in 3 minutes. Oh, it's some like small positive exponent. It's going to depend on beta and eta. Okay. So now I want to explain to you this result that says that uniform lower scalar curvature bounds, in this sort of generalized sense, are preserved along the regularizing Ricci flow. Okay, and this is also going to explain, we touched on this a little bit before, but this is going to explain why it is that we choose beta between 0 and 1/2. And I'm not so satisfied with this, but that's okay. Okay, and so here what we are going to use, as we learned from Robin's talk, the scalar curvature is a super solution to the heat equation under Ricci flow. So we're going to use this fact. And so, okay, so what do I want to show? What I want to show is that if initially I have this uniform lower scalar curvature bound in this generalized sense, then for positive times, every time slice of the regularizing Ricci flow will satisfy this sort of classical lower scalar curvature bound. And so what I will do is I'll prove this by contradiction. So let me suppose that, actually, let's just do it for the lower bound is 0. So let's suppose that for some positive time, there was some time slice of the Ricci flow that had negative scalar curvature somewhere. And then I will use the fact that the scalar curvature is a super solution to the heat equation to show that actually if that were the case, then at an earlier time, at a nearby point, I also had to have negative scalar curvature, okay? And so, how should I do this? So, okay, let's suppose, we have some point at some positive time such that the scalar curvature at x time t, this is a time t, is less than 0. Okay, let's say this is less than negative epsilon. Okay. And now what I want to show is that actually it had to be the case that at a nearby point at an earlier time, I also had scalar curvature bounded above by, minus epsilon plus an error, okay? And so let's suppose that's not true. So let's suppose that actually, even though this is true, at time t over 2, there was a great lower bound on the scalar curvature, okay? So suppose that at time t over 2, the scalar curvature was bounded below by minus epsilon plus, okay, I put a blank space here because I'll have to pick up an error. And we're assuming this is going to hold on ball of radius t to the beta. Okay, so basically t to the beta is the amount that these points are allowed to move apart. Okay, well, if this were true, now let me use the fact that the scalar curvature is a super solution under the Ricci flow. Okay, so if this were true, then I could lower bound the scalar curvature at x at time t by integrating a heat kernel against the scalar curvature at time t over 2. This is going to be greater than or equal to, okay, let me not do that. The scalar curvature at time t over 2, how did I put this? The heat kernel at time t over 2 integrated against the scalar curvature at time t over 2. Okay, t by. Okay, and so actually, I can integrate this. I'm integrating this over the whole space. So let me integrate it within the ball of radius t to the beta. And I will also integrate it outside of that ball because I'm integrating over the whole space. Okay, so this is the same thing. Okay, well, I'll write it again. This is outside of the ball. Sorry, no. Okay, now I'm assuming that inside of the ball, I had a nice lower bound on the scalar curvature. Okay, so in here, I have a nice lower bound on the scalar curvature. I have a blank space. And then outside of the ball, of course, the scalar curvature could be like extremely negative, right? But, it's going to be bounded below negative, something over t. Okay, so this is like a horrible lower bound as t goes to 0, but okay, this is still a lower bound. And then the heat kernel, because we are integrating outside a ball of radius t to the beta, and beta is strictly smaller than 1/2, the heat kernel is going to decay exponentially outside of the ball. Okay. And so to get a contradiction here, I need to pick up an error that looks like this. But the point is that because beta is strictly smaller than 1/2, this is going to decay exponentially as t goes to 0. Okay, so somehow we need to do this iteratively. So I just showed you one step of the iteration, but we'll do this iteratively. Sorry, this is a contradiction. This is a contradiction, okay, because there we go. Negative epsilon is not strictly greater than negative epsilon. Okay. And so we need to do this sort of iteratively at every point, which means that these errors are going to add up and they need to sum to something which goes away. Okay, so this is the reason for beta strictly smaller than 1/2. Okay, so to summarize, in order to prove that uniform lower scalar curvature bounds are preserved along the Ricci flow, we argue using heat kernel estimates. And basically, we use these heat kernel estimates to show that if it were not true, then you could find a sequence of points that were all very close to one another and a sequence of corresponding times that go to 0. And so the points would all converge, to some limiting point, and the times would go to 0, and the points are all very close to each other. And so this would tell you that actually there had to be a point where this beta weak condition had to have failed. Okay, so that was very fast, but I think I'll stop there.